look at a continuation of the last application. We did the spring mass system that was unforced, so basically a scenario where you had some mass on a spring and maybe you like pulled it down or lifted it up and you maybe just let it go or maybe imparted some velocity on it, but that was it. You just let it go and then it did its thing. That's unforced. Now we're going to look at a scenario where there's some external force that's being applied after the fact. And do some problems. I'll just give you a heads up right now. Some of these are a little bit involved, but there's one that's going to be get in the weeds a little bit, but it's kind of interesting, I think, as far as like the type of forcing function that we can deal with. So we're going to do a few of those examples. I've got practice exercises that are posted to Canvas if you click on the link for today's page. I don't have a new assignment ready yet, and actually one of the things I wanted to talk about was if we look at the syllabus, I think it lists, I outlined that there will be like 4 tests. And so the second test kind of has like, I think a natural place to put the second test is to have it be about second order linear differential equations, which is what we're doing now, right? What we've been doing, what the last assignment was about, and this application uses. And I know it feels like we kind of just did one, but I think if in order for things to go as like smoothly as possible, I think it would be a good idea to just schedule, like have another take-home test sooner rather than later. So I can be flexible on the due date. I don't know like what other big things you have coming up in other courses. So if I had something ready by the end of the week, we could be looking at a due date of like maybe Wednesday the 25th, but we don't have to set that in stone right now. Like if you have like a test in 3 classes or something that day, like we don't have to have it be that day. Would I be able? Yeah, I was thinking by the end of the week I might have it posted to Canvas. Like so the 13th. Yeah. That's my goal. Certainly, yes, absolutely by the 16th. My goal is have it up online by the 13th. So right now I'll just put a tentative due date to give folks a chance to look at what's going on in their other classes. But I'll plan on a due date of the 25th, which is a Wednesday. And then after we're done, like probably next week, we'll start our new unit, which is looking at Laplace transforms, and which is another way or a tool we can use to solve differential equations. And we'll find that they kind of make solving a differential equation more of a algebraic problem than just a calculus problem. So before we dive into this, does anybody have any questions? Okay. All right. All right, so the unforced system led to just homogeneous equations. Now we're going to look at the scenario where we have some forcing function. And like we saw in the second order linear non-homogeneous equation section, the general solution or complete solution is of the form you find your homogeneous and your particular and you add them together. When we look at this type of application, that homogeneous equation is usually referred to as the transient part, and the particular is the steady state solution. And the reason is because if assuming that M, B, and K are all positive, like if there's going to be a positive mass, if the damping constant is positive, if the spraying constant is positive, which is a reasonable expectation, the homogeneous solution will approach 0 as T grows large. So that's why we call it the transient part, and then the one that kind of persists over time is the particular solution. So let's see. In this first example, we've got a spring mass system with a spring constant of 6 newtons per meter, a damping constant of 5 kilograms per second, and then we have a 1 kilogram mass. So I'm not going to read any further just yet. This gives us, if the mass is 1 kilogram, this gives us 1 times x double prime plus. The damping constant is the coefficient on x prime. The damping constant is always proportional to the velocity. So that's 5x prime. And then the spring constant is proportional to the displacement, so that's 6x. So there's the left side of this equation. It says that it's lifted up 1 meter and given a downward velocity of 8 meters per second. So let's kind of parse that out. These are initial conditions. So they're not going to be part of the equation, but these are the initial conditions. At time 0, it's lifted up 1 meter, so x of 0 is equal to 1. And it's given a downward velocity of 8 meters per second, so x prime of 0 is negative 8. Now it says, suppose there is an external force acting on the system. We'll assume that this external force is periodic with a forcing function equal to 4 times sine of t, so that's the function on the other side. And we're going to find the position function. So, you know, we read through, kind of put together this differential equation. We should, especially after having completed like the last assignment and going through those last sections, be in good shape to kind of get a start. How do we start a problem like this?
The characteristic function.
Yeah, we want that characteristic equation because it's going to help us get the homogeneous solution.
I was going to say the R thingamajig.
Yes, that's the R thingamajig, yep. The characteristic equation. So what is the characteristic equation for this differential equation?
R squared plus 5r plus 6.
And that's equal to 0. The characteristic equation is always equal to 0. I think this factors. So r plus 3, r plus 2, and we get negative 3 and negative 2 for solutions. So what's our homogeneous solution? We have distinct real roots. Say that again.
We get x equals c1 e to the r1t plus c2 e to the r2t.
Right, so now, for us now, that's c1 e to the negative 3t plus c2 e to the negative 2t. So, you know, there's things we don't know about this, right? I mean, eventually we have initial conditions, so we're going to want to find c1 and c2. What's really important, though, is that this is a non-homogeneous equation that we're starting with. So even when we're finding the homogeneous solution, we're not ready to figure out what C1 and C2 are. We can't use those initial conditions until after we get also have the particular solution and put them together to get the total solution. So what does what's the form of the particular solution? Our forcing function is a sine function. Remember, so like we have that table that tells us how to do it. The general, like the rule of thumb, though, and you can kind of see this as you look through the table, is that you want like some multiple of the forcing function, like a constant times that function, plus all of its derivatives, right? Yeah. So what does that look like?
A sine t plus b cosine t.
Great. So now we want to figure out what A and B are. And what's our general approach there?
Partial fractions?
We could, we could use, sometimes that ends up being used with partial fractions, but the undetermined coefficients is usually what we've been doing, right? We have like this basic form, and then we could find the derivative, find the first derivative and the second derivative, and then substitute into this equation that we started with. So xp prime is a cosine b cosine t minus b sine of t, and then the second derivative is negative a sine t minus b cosine t. So I think we have everything we need to go ahead and plug into the equation and figure out what A and B are. So our equation is x double prime plus 5x prime plus 6x, or that's the left side. I'm going to make the substitution here. X double prime is negative a sine t minus b cosine t, and then plus 5 times x prime. So I want to take this equation in the middle, right, this function, multiply that by 5. So I'm just going to go ahead and just do the distribution right off. So this would be plus 5a cosine t minus 5b sine t. And then plus 6x means I'm going to take xp, or x particular, and multiply that by 6. And again, I'll just go ahead and distribute it now. So plus 6a sine t plus 6b cosine t. And all of this has to equal 4 sine t, right? All of this has to be equal to the forcing function. I'm going to simplify that big expression in the middle, right? What we got when we substituted our function and the derivatives in. And I'm going to do it by gathering my sine terms and my cosine terms together. So let's figure out what the coefficient on sine is. So for sine, we have negative a plus 6a, which is 5a minus 5b sine t. I'm going to combine them like that. Is that okay so far? There's a lot of like keeping track of like how many of each function you have. So be vigilant as you work through this, and please, if it looks like, if you're not sure how I got something, or it looks like maybe I missed something, like just speak up right away. It's easy to make mistakes. Like combining like terms is obviously like a simple thing to do, but it's also really easy to make errors. So now for the cosines, we've got minus b cosine plus 5a cosine plus 6b. So for the b's, negative b plus 6b is 5b, and then plus 5a. So I've got plus 5a plus 5b cosine t, and that's all equal to 4 sine of t. How does this help? Like, if we look at this equation, yeah.
The 4 has to be equal to 5a minus 5b.
Yeah, right, the coefficients, right? This is the undetermined coefficient, so the coefficient on sine on this side has to be equal to the coefficient on sine here. What about that other coefficient?
It'll equal to 0.
That has to be equal to 0 because we got no cosines on the other side. So 5a minus 5b is 4, 5a plus 5b is 0. And we have a nice system of equations. This one, I think this system is kind of just begging us to solve by elimination by addition because we have the nice coefficients on the B that cancels each other out. So we got 10A is equal to 4, or A is 4/10, 2/5. And then B, I guess, negative 2/5. Yeah, actually, I guess it's probably simplest to see that if you look at the second equation, right? So B has to be negative 2/5. And so this means that our x particular is 2/5 sine t minus 2/5 cosine t. Now we're not quite done. I mean, we've done a lot of work. We found the particular, but the complete solution or the total solution is we're going to take the homogeneous plus the particular, add them together. And don't forget, we have initial conditions. So once we have x of t, then we can use our initial conditions to figure out what C1 and C2 are. I'm going to go start that process on the next page. So C1 e to the minus 3t plus C2 e to the minus 2t, that was our homogeneous, and then plus 2/5 sine t minus 2/5 cosine t. So we want to use those initial conditions. What do we do? Yeah, let's take the derivative so we can use. Oh, so say it again.
Find x prime of t.
Yeah, we're going to find x prime because we obviously have our x of t, but we need x prime to use that initial condition. And this derivative isn't too bad. There's no product rule to worry about or anything, just some individual terms. So we have minus 3 c1 e to the minus 3t minus 2 c2 e to the minus 2t plus 2/5 cosine t plus 2/5 sine t. Okay, one of our initial conditions was that x of 0 equals 1. So I'm going to use that in this equation. When I worked this out earlier, I had to do it twice because I put the wrong initial condition. I put it into x prime instead of x, so I'm just being careful. There's a lot of ways to make errors here. So 1 is equal to, what remains? Like what expression do we end up with when we plug in 0?
Definitely C1 and C2.
Say that again, Ben?
Definitely C1 and C2.
So we have C1 and C2 because the e to the 0 is 1.
Minus 2/5.
And then minus 2/5. Yeah, because like the sine of 0 is 0, cosine of 0 is 1. So we just have those coefficients left. So that gives us the equation C1 plus C2 equals 7/5. And I'll leave that there for now. So we have one equation with two unknowns. Then they also tell us that x prime of 0 equals negative 8. So, okay, so now we're plugging it into the x prime. What remains when we plug in 0?
Negative 3C1 minus 2C2 plus 2/5.
Plus 2/5. Right, again, because the cosine term becomes 1, or cosine of 0 is 1, and the sign drops out. Great. So I could rewrite this to say, let's see, 3C1 plus 2C2, if I throw those over on the other side, and then add 8 to both sides. So 8 is 40/5 plus 2/5 is 42/5. Okay. So we have a system of equations we need to solve again. And we could do it by hand without too much trouble, I think. I'll take this top equation and I'll multiply it by a -2, and I'll leave the bottom equation as is. So when we add those together, the C2 terms cancel. We end up with just C1 equals 42/5 minus 14/5. 28? 28/5. And then I think I would use maybe this equation here. Just seems easiest to find C2. So that'll be, C2 will be 7/5 minus 28/5, which is -21/5. Okay. So let's put it all together. Our position function or displacement function is 28/5 e to the minus 3t minus 21/5 e to the minus 2t. And then, right, plus 2/5 sine t minus 2/5 cosine t. This is the, this is the position function or the displacement function. The first two terms, that was from the homogeneous. This is what we call the transient part, because it goes away, right, as t gets large. Those are exponential decay functions. Like, it kind of has an effect on the position at first, but then it just, as time goes on, has no effect at all. And then this is the steady state, meaning over time, this function behaves just like the particular. You can't even tell that, like if you look way out, you couldn't even tell there was another part of the function. And as long as that forcing function, like 4 sine t, as long as that function is in effect, if we assume it goes on forever, like this will be like its forever position. How's that? So that one was like a nice, I would call it kind of a warm-up problem. We didn't have to worry about any product rules. We had nice linear systems to solve, right, that were pretty simple to do by hand. And just sort of a nice overview on like how we solve these non-homogeneous equations. The next one is actually going to stretch us a little bit. What's that? Yeah, so the behavior is, the behavior as t approaches infinity, that is basically the steady state. Right, that we mentioned that the transient part of the solution is kind of tends to 0 as t gets large, and the steady state solution is what persists. So here's the thing that's going to make this example challenging, but also maybe interesting, is look at this forcing function. But we're obviously going to find the homogeneous first. But there's no, if you look on that table, there's nothing that says, here's the form you use when your forcing function looks like this. We have separate ones for e to the stuff. We have separate ones for sine of stuff. But when we have that product, we don't have like a rule in the table. But basically, here's how it works. So we'll notice, by the way, it's the same spring mass system. It just has a different forcing function. So this part on the left side is the same, which means the homogeneous solution is the same. It's got the same characteristic equation, so we don't have to find that over again. So we know that xh of t is c1 e to the minus 3t plus c2 e to the minus 2t. We don't know the values of c1 and c2. We found them for the forcing function in the last one, but a different forcing function means that you're going to get different values for these constants. What we need to do now is say, okay, well, what form should that particular solution take on? And when we use, when we're going through with this technique, when we're using the method of undetermined coefficients and just trying to say, okay, I think my forcing function should take on this form, the basic rule behind all of that, and maybe actually I'll go back to, okay, here we go. So here's the table, right, that we've all been using. The basic rule for how you get the form for the particular is that you take the forcing function, like it's some multiple, some unknown coefficient on the forcing function, plus all of its derivatives. That's why when it's a times e to the bt, your forcing function, the exponential is its own derivative, right? So I'm just going to need that same function right back. Sines and cosines, you could keep taking the derivative forever and ever and ever, and it's just going to cycle through sines and cosines. With polynomials, you take the derivative and you just keep getting the smaller powers of t until you get to 0. So that's why if we have any polynomial of degree n, that particular solution is going to be a general polynomial of degree n, with just some unknown coefficients. So now, if we think about our forcing function here, if we take the derivative, we just keep taking the derivative of this forcing function, 4e to the minus 0.2t times sine t. In fact, maybe let's just take the first derivative and take a look and see if that helps guide us toward the right form. What makes this difficult is, of course, we take the derivative, we need to use the product rule. It doesn't make it difficult, but it makes it a little bit more complicated. So what do we get? Negative 0.2 times 4 is negative 0.8 e to the negative 0.2t sine t, and then plus 4e to the negative 0.2t times cosine t. There's just the first derivative. Now, if I imagine continuing to take derivatives, here's another product rule in the first term, but I'm going to get something just like what I got. The only thing that's going to be different is the coefficients in front. And on this one, well, the difference there is I have a cosine instead of a sine, but I'm still just going to have like sines and cosines. Sine times that exponential, cosine times that exponential. I keep taking the derivatives as much as I want, and I'm only going to end up with terms. I'm going to have a collection of terms that look like some constant times e to the negative 0.2t sine t, and then some other constant e to the negative 0.2t cosine t. Even though like the derivatives, they eventually get kind of messy because we have to use a product rule over and over again, I know what the kinds of terms I'm going to have. So when we use that rule of like take that function plus all of its derivatives, it's just going to look like a times e to the negative 0.2t sine t plus b e to the negative 0.2t cosine t. So to figure out a and b, we need to find x prime and x double prime. And I think to make it just a little bit, a teeny bit easier, I'm going to factor out the e to the minus 0.2t, because then I only have to use the product rule once. So now we use the product rule. I'll take the derivative of the first times the second, so that's negative 0.2 e to the minus 0.2t times the stuff in the parentheses. And then the first times derivative of the second. We need to take the derivative again. To make that a little bit easier, I'm going to factor out the e to the negative 0.2t again. I'm going to do a couple of things, actually. I'm going to factor that out. And then I'm going to distribute the minus 0.2 here. And then there's nothing else to distribute in the other group. But I want to kind of gather my sine terms and my cosine terms. So I've got a negative 0.2. Let's focus on the sine first, the sine terms. I've got a negative 0.2a times sine t, and then minus b times sine t over here. So overall, I've got negative 0.2a minus b times sine t. And then if we do the same thing with the cosines, we've got negative 0.2b and then plus a, so a minus 0.2b. And now we get to do it again. But at least there's not going to be a third derivative. I'm going to stop for a moment and just give everybody a chance to kind of either catch up or look it over and see if it looks kosher to y'all.
There probably already is.
He's saying that we should just do this with like a
I'm
a
saying
program.
as a software engineer,
Mhm.
you should totally write a program.
Oh, okay. Ben was suggesting that any software engineers in the class could write a program to do it for us. They do exist, although writing the program yourself would probably be pretty fun. Wolfram Alpha or Mathematica or MathCAD would do it. But that would also, I just want to say, take all of the fun out of it. And I think part of my job is to make sure that we retain that sense of wonder and joy when we're doing this. You know what? I think of that, right? Like how there are programs that can do some of this stuff for you. And when I think of that, and then I think of like, oh, but I kind of like doing it by hand. All I could do is think of, wow, when people were developing this in like the 1800s, like they must have been like just super paying attention to detail. Like there's a lot of like, there's a lot of detail in this and opportunities for error. All right, so let's do the second derivative. I'll take the derivative of the first guy first, so minus 0.2 e to the negative 0.2t, and then the stuff in the brackets. And then e to the negative 0.2t. And now we're going to take the derivative of what's in the brackets. But, you know, I'm not going to get too hung up on like those coefficients right now. Just like the stuff in the parentheses, like negative 0.2a minus b. That's just a coefficient. It's a constant in front of the sign. So when I take that derivative, I'm going to get negative 0.2a minus b times cosine. And then, let's see, the cosine is the one where the sign changes. So that'll be minus a minus 0.2b cosine t.
Isn't it sine? Yeah, it'd be sine.
Oh, yes, thank you. Yep. Good eye. Okay, we're going to simplify this. We're going to grab the factor of e to the minus 0.2t, put it outside like we did on all the other ones. And now I'm going to do what we did before. I'm going to just try to gather what's my coefficient on sine overall, what's my coefficient on cosine, keeping in mind that we're going to distribute this factor of negative 0.2 to that first, through that first set of brackets. So maybe I should do this in a couple of steps, because I feel like if I do it all in one step, that will be tempting fate. So that'll be what? 0.4a plus, sorry, 0.04a plus 0.2b. And then plus negative 0.2a plus 0.04b. And then nothing to distribute through the next one, so I'm just bringing those terms down. And I think what I'll do here is, I think it might make it easier. I'm going to write this as plus and then negative a plus 0.2b times sine t. Okay. So let's figure out our coefficient on sine first. So there's a sine coefficient. Here's a sine coefficient. Overall, let's see. Yeah, but I want to collect, so I'm gathering the sine terms, and then within those coefficients I have some like terms. I've got so many a's and so many b's. So I've got positive 0.04 a and then a negative a. So 0.04 minus 1 is a negative 0.96. And then plus 0.4b. And then for the cosines, how many a's? Negative 0.4a. And then 0.04. They won't, because they're one's on sine and one's on cosine. But 0.04 minus 1 is a negative 0.96 b cosine t. Wow. There's our second derivative. So we started with the basic form. right, for the x particular. Why did we find the derivatives? Like, what does that help us do?
The general solution.
It does, but like before we get that, right, there's an intermediate step. Like, what in particular are we going to do here? What are we going to do with these derivatives that we found?
Implement the function.
Yeah, we need to find a and b. So like we're going to take the x prime, the x double prime. We're going to substitute them into the equation and set it equal to the forcing function, and then use some algebra to find a and b. Let me just see. Okay, so I've got pretty good on space right now. So the equation looks like x double prime plus 5x prime plus 6x. And I'm going to substitute. I'm going to do this in 3 lines, just I think to make it easier to deal with. So x double prime, that's what we just found. I'm going to write that down first. And then I'm going to add plus 5 times x prime. And x prime is this function up here. And then plus 6 times the function itself. The function itself was e to the negative 0.2t times a sine t plus b cosine t. Okay, so I'm adding all of these together. Again, all 3 of these have that common factor of e to the negative 0.2t. I'm going to pull that out. Then let's put together our coefficient on sine. And I'm just going to add that, plus 5 times that, plus 6 times that. I'm going to not forget to distribute. So if I distribute the 5 through the x prime, through the negative 0.2a minus b, we have minus a minus 5b. And then our last term is b plus 6a. And that's times sine of t. And for cosines, again, I'm going to make sure that I remember to distribute the 5 through the x prime coefficient and the 6 in the function itself. So we have negative 0.4a minus 0.96b, then plus 5a minus b after I distribute the 5, and then the last one I get plus 6b. And now we're almost done. I'm just going to combine like terms. I'm going to stop there though first. and see if there are questions on how we got this far. Okay. All right. So we have e to the minus 0.2t times. And then negative 0.96 minus a plus 6a. Negative 0.96 minus 1 plus 6 is 4.04. So we have 4.04a. And then negative 5 plus 0.4 is negative 4.6b. Sine t. And then similarly, if you combine like terms for the cosines, we get 4.6a plus 4.04b. And this right here is equal to 4e to the negative 0.2t sine of t. Where does that come from?
That's the forcing function?
Yeah. Yep, that's the forcing function, right? We find the x prime, the x double prime, we substitute everything in, and then in order to check that the differential equation is satisfied, when I substitute it in, it has to equal the forcing function. Okay. We've got some algebra, but some of this algebra will be made easier through the use of a calculator. There's a lot of problems that require 2 pages. I'm going to hold up a minute. What's that?
We can get rid of the e.
Yeah, can you turn on your mic and say that again?
We can get rid of the e minus 0.2t on both sides.
Yeah, like basically, essentially what we're doing is dividing by e to the negative 0.2t on both sides. Because e to the negative 0.2t is never equal to 0, we're allowed to do that. So I'm going to just scroll down to the next page. So we find that we said let's get rid of the e to the negative 0.2t on both sides, which I agree with. So that gives us 4.04a minus 4.6b sine t plus 4.6a plus 4.04b cosine t. And since I've canceled out that e to the negative 0.2t, on the other side I have 4 sine t. All right, what does this get us? What's something we can say for sure?
4.04a minus 4.6b equals 1.
Yeah, and how do you get that?
It's the same coefficients.
Right. Yeah, we're just comparing coefficients. So 4.04a minus 4.6b equals 4. And what does 4.6a plus 4.04b equal? Yeah, because there's no cosine term in our forcing function. Now, when we were doing, when we ended up with these systems of equations before, we had nice integer coefficients, and that made it pretty convenient, which we're not really in that position right now. But we can go ahead and use the calculator. There's a nice feature on the calculator. We can enter this into a matrix. And if you took pre-calc here, you did some stuff with matrices, maybe you saw Cramer's rule. If you did and it was a long time ago and you forgot, or you didn't take pre-calc here and you don't know what Cramer's rule is, that's fine. I'm going to show you right now. Here's how we put this into a matrix. Really, if you have a system of equations, as long as, here's what's important. I kind of have a column, like I have my A term first and then my A term. I've got the B term and then the B term, and then I've got my equals and then the constant. So that system is in the standard form. And then the matrix looks like this. I'm just going to strip the variables out and just write the coefficients. So 4.04, negative 4.6, 4, and then 4.6, 4.04, 0. There's our matrix. Usually we write a little, draw a little vertical line where the equal signs would go. I'm going to show you how we can enter this matrix in the calculator and use a function that'll just solve it for us. I mean, I don't want to deprive you of the fun of doing the linear algebra, but I feel like these are really inconvenient numbers. So on the calculator, if you have a TI-83 or TI-84, there's a matrix menu, which is like above. In mine, it's written in blue. But it's that button that appears red on my right now. You have to hit the second button first. And that gets you into the matrix menu. And what we're going to do is edit a matrix. I'm just going to go ahead and put it in the first matrix, matrix A. The first thing it wants you to give it are the dimensions. And dimensions are always number of rows by number of columns. So our matrix here has 2 rows and 3 columns. So I'm going to do 2, 3, and then once I put that in, you'll see that there are exactly the right number of spaces for me to plug everything in. And then I'm just going to put in the values. After I punch in a value, I'm going to hit enter. It'll bump me over to the next cell. So 4.04, negative 4.6, 4, and 4.6, 4.04, and 0, which we already have. So now I've got this matrix in here. And we're going to, the next thing we're going to need to do is access a feature or a function, a matrix function, through that matrix menu. But I'm going to quit to home first because I don't want it to think that what I want to access is what I want to put into the matrix. So I want to make sure I'm out of this editing, the matrix editing window. So now I'm back at home. I'm going to hit call matrix, and now I'm going to do some math. So I'm going to use the arrow key, call up the math. And I'm going to go scroll down. I'm going to scroll down quite a ways. There's an option called RREF, which stands for Reduced Row Echelon Form. And Reduced Row Echelon Form is a long way of saying, show me what the answer is. It'll just, once we run this on the matrix, we'll just know exactly what the solutions are.
Sorry, there's a home button on this one?
Oh yeah, so sorry, you quit to the home screen, so it's second quit. You hit the second mode, and that quits you to the home screen. Math. And then it's, on mine, it's item B, so you got to scroll down quite a bit. RREF. Yeah, so now I'm going to hit enter. I've got that here right on the home screen, and now it's waiting for me to tell it what to use, what matrix to plug in. So I got to go once more into the matrix menu. So second matrix. This time just under names. I put my matrix in matrix A, so I'm going to hit enter, closing my parentheses. And there's my solution. It's in reduced row echelon form. Notice the first 2 columns are 1, 0, 0, 1. Wherever there's a 1, that top row tells me that 1 times A is equal to 0.4311, blah, 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 blah. The second row tells me that 1 times B is equal to negative 0.4909, and so on. I'll just use 4 significant digits, I guess. Negative 0.4909. So now we have our particular is 0.4311 e to the negative 0.2 t sine of t minus 0.4909 e to the negative 0.2 t cosine of t. Oops. So far, now our x of t solution, we're going to add the homogeneous and the particular. So we have c1 e to the negative 3t plus c2 e to the negative 2t plus, and when I write this out, I think I'll grab the e to the minus 0.2t again outside, factor it out, rather. So times 0.4311. Oh, 9 cosine t. What's left to do?
Solve for C1 and C2.
We need those initial conditions, so we're going to find one more derivative. But it's only the first derivative. We don't need any second derivatives. It'll be okay. Don't worry, everybody. So we got minus 3 c1 e to the negative 3t minus 2 c2 e to the negative 2t, and then product rule. So negative 0.2 e to the negative 0.2 t and plus e to the negative 0.2 t and this will be 0.4311 cosine t plus 0.4909. Hold on. I'm going to just nudge this down onto the next line so I don't have to write it all cramped. Great. X of 0 was equal to 1, I think. Yes, positive 1. So using that on this function up here, plugging in 0, boy, I'm glad it's 0. They gave us those conditions for.
I feel like most of the time it's like
Yeah, I mean, time is like a relative, so start the clock at a convenient time.
Yeah.
Yeah. Okay, so when we plug in 0, we get C1 plus C2. And then the sign goes away, so negative 0.4909 minus. So C1 plus C2 equals 1 minus 0.4909 is 0.5091.
Isn't it plus?
Oh, yes, thank you. It's plus. Yep, yep. Oh, I don't need a calculator for that. 1.4909. There we go. Pretty sure I can do that one. And x prime of 0, that was -8. Okay, so this time we're plugging into this one. So we have minus 3c1, minus 2c2. And then, let's see, got to be a little careful. We've got to distribute the -0.2 to the -0.4909 there. So that's 0.09818 plus 0.09818. And then plus the 0.4311. And this gives us 3c1 plus 2c2, if I throw those on the other side, is 0.09818 plus 0.4311 plus 8, or 8.52928. So here's our system of equations that we're going to solve, which you could do on the calculator or by hand, but I'm going to save you the trouble and tell you what I got when I did it earlier. I got C1 is 5.54748. And C2 is, what's that? Like I threw these on the other side and then I added the 8 to that side. Whoops. For C2 I got negative 4.05658. And finally we could put this all into the function. Particular there's our function. We worked hard for that one. So in this case, the first part here, this is the transient part, what we call the transient part, and then this is what we generally call the steady state. But the transient part we call transient because it's exponential decay functions and it approaches 0 as t grows to infinity. What happens to the steady state solution? Well, so the stuff in the parentheses, that's sort of periodic in nature, but that's being multiplied by e to the negative 0.2t. I mean, whatever happens, as t gets big, whatever happens to this stuff here, that sine and cosine part, it's bounded, right? I mean, sine and cosine are both bounded, so that reaches some maximum and some minimum. And then as t gets huge, that's just going to stay within those bounds, but it's being multiplied by this thing. What's that approaching? Say that again? Well, it's a negative 0.2t in the exponent. What does a negative exponent mean?
Just one here.
It's getting smaller, right? A negative exponent means you're dividing by it, right? That's the same as 1 divided by e to the 0.2t. So that's another exponential decay. It's an exponential decay factor that's a part of that steady state. But this, as t approaches infinity, the mass approaches equilibrium and will just keep getting closer and closer to equilibrium until it gets so close that we probably just can't tell the difference and say it just kind of stays there, stops moving. So as t approaches infinity, x of t approaches equilibrium, or the mass approaches equilibrium. We can see this if we graph it. So here I've already put it in the calculator, and I'm graphing it from 0 to 15 seconds, from -1 to 1 on the y, and it looks like that. Maybe we could have had a suspicion at the get-go that it would do something like this. The forcing function was periodic, but also decaying exponentially. I mean, from the very beginning, looking at this, it had that periodic factor of sine t, but we were multiplying at that forcing function by an exponential decay. We know that as t increases, that forcing function itself is going to approach 0. So it maybe is not so surprising that the position approaches 0, that it approaches equilibrium. Questions? Okay. We got one more, which we might not finish, but I think we can get at least a start on it. In the ones that we've been doing, they kind of describe the situation, and we set up the differential equation. What we're going to do in this example is they've given us a differential equation, and they want us to interpret it. Now, there could be multiple interpretations, right? I mean, they haven't given us a context, but in this section, if I wanted to interpret this in the terms of a spring mass system, we could say could be interpreted as a forced spring mass system. I know it's forced because there's a forcing function there. Now, when in a spring mass system, there's a few things we want to identify. The mass, the damping constant, and the spring constant. So what's our mass here? Say that again. Note, 2, whatever, the coefficient on x is the spring constant. The mass is the coefficient on x double prime. So 0.2, and I'll just, again, they haven't given us a context, so I'm just going to say, let's impose metric units, so a mass of 0.2 kilograms. And we have a spring with a spring constant of 2, newtons per meter? That's what we usually call K. And then a damping constant. The damping constant is always proportional to the velocity, so that damping constant is 1.2. And I think those units are like Newton seconds per meter or something, or maybe kilograms per second, depending on whether you're using newtons or kilogram. What about this stuff right here? In fact, maybe let's just start here. What does that tell us?
Second, critical.
Mm-hmm. So we could say in this x of 0 is negative 0.5, so that would mean that it is, what, pulled down half a meter?
Yeah.
And then, so we have an initial position, and then the next question is, was it just let go, or was it pushed? Was it given some initial, like, velocity, or did they just let it go? And how do I tell?
So it has to do with the x from 0 and
Mm-hmm.
or say that another way. It has to do with x from 0 equals 0.
Yep. So if x is the position function, x prime is its velocity. So that's what what that tells us is that it wasn't pushed, right? It wasn't given an initial velocity, it was simply released. And then the one thing that we haven't, I guess, explicitly mentioned or written yet is that there's an external force acting on this of 5 times cosine 4t. And that is periodic. So we're pretty close, I guess getting close to the end of our time. We did the first part. We did the interpret. So when we come back on Wednesday, we'll solve this initial value problem. It won't be nearly as involved as the last one because that forcing function is a little bit simpler to work with. Yep. So enjoy the rest of your day, and I'll see you all again on Wednesday. I'll be in Williston.